Well, in chapter two, one of the big things we talk about is gravity. Wow, what a term, gravity. The big problem that you see with gravity is the fact that people don't understand it's here every day. Any building that is built is coming down right around you. And the big thing is that when you start looking at this, Brannigan brings up a good point. A building is being pulled every day to the center, meaning the earth. So gravity is important. One of the big things you want to look at is loads. Look at the difference that are going on in the loads today. We've got stress and strain on the building. If you start measuring stress and strain, you start looking at a kip equals 1,000 pounds. And the strain is actually the elongation that occurs or deformity that starts to occur with the building materials. The big thing is force. Look at the force. You're looking at compression, tension, and torsion. One of the big things is, look at the Golden Gate Bridge. It's all those put together. Tension being the cables holding the building up. Compression is the long standing towers that are put down against the concrete forms. And then you got torsion, which is the elongation of the bridge itself and how it torques back and forth. And those are all key indications of the type of forces that you run into. Every one of you has seen a dead load. That's generally we see air conditioners on the roof and other HVAC components on a roof. It's all a dead load. And under fire conditions, we have the serious issues that go on there. The big thing about live loads is they're moving. It's like inertia. Once it gets going, it stays moving. Your body is a live load. And the big things is concentrated loads account for the large heavy loads in the building, but a large load it has to be calculated for too. And what do we mean by a live load? How about floors in a hospital when they're moving gurneys back and forth? Those are live loads in motion. The other thing is, what about live loads in firefighting? We got water trapped on the roof, fire equipment on the scene. It's all part of those important things that go on. An impact load. We see this once in a while, cars into the building. That's an impact load. You have lateral impact loads, where you might have one part of a building be hit, and also at the same time the building next to it suffers an impact because of debris going back and forth. Static and repeated loads are next, and those are real important. Static loads applies stress or load pressure over a period of time. It's constant and it's heavily safe. The other thing is repeated loads. They are applied intermittently, and it's just like a bridge crane rolling across the top of a factory. It's an intermittent load. One of the biggest things you got to look at, and this is one of the things you see, is a wind load. Today's building construction has to deal with a hurricane rating, and you start seeing straps applied to roof trusses that tie the roof truss itself to basically the top of the beam or the top of the column, or what we would call in this case the wall, and it ties it all into place. And what it does, it keeps the roof in a situation where the roof may have a wind load that comes up, it brings it right back down, it doesn't lift off. Wind loads are applied on small buildings, but masonry buildings are less susceptible because of how they're built. So you don't have a real problem with wind on a masonry building because it's basically brick and mortar holding it together, and most of the time you got a steel infrastructure going on as well. So wind loads become very important, and the problem is we're looking at wind loads as part of a portal bracing, concrete walls, tube construction, which was in the World Trade Center building, and core construction. So you've got some different loads here, and one of the problems with tube and core construction is it's built around a frame, and what happens is if that tube construction or core construction starts to collapse, the building itself starts to collapse. So you got concentrated loads, you've got axial loads, you've got all types of loads to look at in this chapter. Fire loads are really important, and one of the things that we talk about, and one of the things when I have you address a paper or something, start thinking about fire loads. Start thinking about the heat release factor, the Q and a caloric value that's going on in a fire. Some of you have been in the fire service for a while, and some of you are now entering in the fire service or just shortly in it for a couple, 3 or 4 years. You're not seeing the fires that we've seen earlier in our careers. And what's happening is the hydraulic measurement of water against a fire load today is not much different than it was when we started. But the problem that you have now, the heat release factor is greater. And what you're seeing is synthetic materials and all those components now that heat up quickly and create what we call, in my case, I call it a heat phenomenon or a fire phenomenon, and it's rapid buildup of heat, and the next thing you know, you have degradation of a structure. So these are all key things that you got to look at. You got suspended loads. Look at the next time you go into any restaurant. The ceilings are all suspended loads. Sometimes you go into a high-rise building and you'll see suspension items hanging from the ceiling, and that's a suspended load. Big thing is there's safety factors involved in all this. And the big thing is it has to be a calculation. You got to look at the calculation of the weight, what the ceiling factor is going to hold that. So it's all by design. None of us have the time on the scene with a calculator to sit there and say, wow, that airplane hanging from that ceiling in that high-rise building's lobby, it weighs this, this, and this, and under fire conditions is going to do that. Those calculations are done before you walk in the building. The architect and the engineer that is on the scene there, and the structural engineers, have to design the building to a safety factor, and it's really important. One of the big things we're dealing with today is composite materials. Everything today has some sort of composite factor to it. Whether it's brick or a composition wall, or it's concrete or steel, there's definitely a composite part to this whole program. Structural elements, in this particular thing, you're seeing columns, how they've been arched, how they also are, weight is transferred through the arch and through the beam. And it's important to understand there's a law, it's called Euler's Law. And that law tells you what your weight factor is going to be on columns from where the beams are placed, and how that beam is going to put weight on the column. A good example, when you start looking at beams, next time you go to a open concept mall, when you see a large beam going across a span where there's 2 entranceways, the beam is sitting across an opening supported by 2 columns, which is each side of the wall. And the big thing is you got to look at the deflection of the beam, the neutral axis of the beam, and the stiffness. The stiffness is really important. If the beam bends like this, okay, what happens is that's got to be a calculation there. And the columns, well, on this side and this side, and with that going like that, there's a comprehensive ratio put in place of that to show you that the columns are going to hold the beam up like this. This is the beam going across. These are the columns. My hand's like this. Those are columns. And the big thing is by doing that, you'll see how that can be supported and how it holds its weight. Now, the factor comes when those columns are disturbed, or you start seeing additional weight put on the beam, and you start seeing a bow effect like that. That goes to show that the beam is being stressed past the calculations rated for. Here's a good example in your book. This is probably the best thing in this chapter in regards to showing the depth of the beams and the capacity. It gives you a pretty good idea of what you can do in a load. You can see the short beam, the 6-foot beam, the 12-foot beam, the 18-foot beam, the 24-foot beam, and the 36-inch beam. As they get bigger in span, the less the weight the beam can support. So the 36-foot beam can only hold 550 pounds. So you can't put any weight on it. So the big thing is you got to look at how all this comes together. Naturally, there's a definition of all the different types of beams, and it goes on to tell you all that. Beam loading is how you start looking at distribution along the long axis of the beam and the concentrated load that could be in the middle. So you got to be careful what you do there. The other thing is reaction and bending. It's all part under heat. One of the biggest fires that I had years ago was the Carousel Inn on Reading Road. It wasn't the first fire we had, it was the second, actually the third fire we had there. And this was in the back part of the building where we actually seen I-beams that were probably 24, 25 foot spans, and they're probably every bit of, I would say, 24 inches in a span width as far as the thickness goes. And we watched under heat conditions how those things twisted like pretzels under heat conditions. So it goes to tell me when you have a temperature, steel starts at about 800 degrees where it starts softening up. So when you're looking at a fire of 1500 to maybe 2000 degrees, steel's doing one thing. It's stretching and it's twisting at the same time. So the reaction and bending becomes a very important part under fire conditions. Columns, again, we talked about that. Here's a good example. These are like Paratex shores for columns, struts or rakers. They're used to hold the building up when the building starts falling apart. You got to understand that the decrease in load carrying capacity, a 12-foot column versus a 6-foot column, what do you think is going to be stronger, a 12-foot column or a 6-foot column? Well, let's talk about the span. How tall is the column? How is gravity affecting the column with a beam on top of it? Is it 12-foot? Is the load being transferred down longer? Or is the 6-foot column beam a shorter span and you have an increased amount that you put on there? I would say when you start looking at a 12-foot column beam, it starts to decrease as you go down all the way. Shapes of columns, wooden columns, the types of columns are all in there. And the walls, the very different types of walls. I want to get to the end of this PowerPoint just to get to some things to look at. We're seeing a lot of arches in buildings again. Arches are very great, but the problem is, look how they're built. In most cases, arch is formed and material is basically put around the arch. If it's concrete, it's plastered over it. That they don't bring in a concrete arch unless it's molded or cast in place. So that means they have to build the jig, as they call it, and put the frame together and put the arch and pour it in concrete. Then they place it in the building. Rigid frames, hard shells and domes, these are all important. I want to get to this slide more than anything else. Connections. The next time you're in a building and it's got an open truss assembly inside, look at the connections. One of the most dangerous things that happened in my span is in a training in a vacant buildings. It was a manufactured building, and the big thing was this an industrial complex, and we had a building with no heat in it. It was the middle of winter. We were training, and what happened was we had basically a makeshift office in the center of the building that basically caught fire accidentally in our training. We were smoking the building up. What it did, it created so much heat that the connections, because it was cold outside, when they started to heat up, they failed and the roof assembly came down. That was a pretty dangerous day in my life as far as firefighters could have been trapped and killed. So you got to look at the big picture and how all this comes about. One of the biggest things I can tell you right now is this chapter is probably the best chapter in the book, and you're looking at how things go together. So I hope you enjoy it, I hope you like it, and I'll be following up again. Thank you.